Hi, my name is Steve Ulrich. I'm with Arista Networks. I help folks fling bits. I'm here to tell you that IGPs are cool again. So here's a little bit of an overview about what I'm going to talk about. Over the past few years, there's been a whole lot of activity in the data center, routing protocol space. We're in the process of refactoring all sorts of nibbly bits inside of the IGPs from a resource and application announcement perspective. And there's a whole lot of activity going on here, largely driven out of work that's going on inside of data centers. No doubt you've seen several presentations around using BGP inside of your data center. I'm going to talk about some trends we're seeing in the networking industry at large around how folks are building networks, the strains this is putting on to kind of traditional IGPs. Some of the work that's going on inside of data centers from, let's see if we can improve the situation from a routing protocol perspective, and then talk about a generalized approach that we've been working on from an industry perspective in terms of just making, notably I'll focus primarily on ISIS, but this work is being extended across a range of protocols. So a bit of background, from an IGP perspective, the historic deployment model has looked a lot like what's on the left, right? Sparse environment, a lot of wide area links. We've kept the topology fairly straightforward and simple in terms of fan up by using big lags as we go from metro to metro. But what we've seen is an explosion in designs like those on the right. This is from Facebook's F8 presentation where they talk about what they're doing in their data center and their campus backbones from a data center perspective. And what you'll note here are multi-stage cloth fabrics. And IGP scaling limitations have really driven us towards using BGP as the de facto IGP for data centers because of all of these links. You'll have tens of thousands of links in a data center environment. And at that scale, the LSA and LSP announcement tends to eat itself alive. Now, we've been very successful as an industry doing this with BGP, but we're kind of overloading some of the behaviors of the protocol, and we're also losing things that are really valuable from an IGP perspective. Further, this scale-out or CLOS-based approach is making its way into kind of service provider backbone environments more commonly. And there's a few things that are driving that. There's economics that just kind of surround, kind of big, classic big box deployments. On the left, we have kind of your standard POP model where you've got, edge, you've got, a couple of core routing devices which are vertically scaled. And, coming from a traditional, networking vendor, we've built really big fridge-sized boxes in order to facilitate these kinds of deployments, but there is a upper bound in terms of the scaling profile that can be achieved with these platforms. And so what we've been seeing and what we've been supporting here is a scale-out design where we're taking these data center design principles of leaf-spine networks and cloth fabrics, and we're building that out. But now we're creating a new problem where we have a very large number of links that are now starting to show up inside of our service provider backbone IGPs. So like with all the stuff that's to love about the right-hand side of the picture, how do we start to address some of the gotchas that go along with this from a control plane perspective? And that's what we're working on here. I would like to take this time to point out a couple of things that are really nice about this and some of the challenges that we're also seeing with the fridge approach, right? The fridge approach is getting increasingly power prohibitive. It's very difficult to find sufficient power in POPs or in certain environments to deploy vertically or vertically integrated systems. So going after these kind of scale-out designs lets us go in and right-size and actually grow our power footprint in parallel with what we're doing from a service delivery footprint. But this is just kind of shifting this problem space into a different direction where we were kind of consolidating all of these links into the backplane of a routing device. Now we're blowing up the routers and we're moving the control plane problems elsewhere. So let's talk a little bit about some of these scaling problems. As I mentioned before, we're using BGP primarily in these massively scalable data centers. And the nice thing here is there's a ton of different BGP implementations out there. So you've got your pick of the litter in terms of what protocol implementation you want to use, what your automation framework looks like in terms of cohabitating with that particular BGP daemon, and if you know what your configuration, your deployment model is going to be, the configuration is totally automatable and it's very predictable. And then we get to kind of lean back on using ECMP so that we can kind of limit the impact of convergence events. We've got opportunistic forwarding across a bunch of links inside the data center. But we're also losing some things. You can't use this in an arbitrary topology. You can use this when you have a symmetric bipartite graph. You can't really automate arbitrary topologies with BGP. It's great for expressing policy and for doing edge routing and distributing prefixes around the network, but I'm losing all the visibility into what the network is actually capable of doing. And increasingly, we need to insert these dense graphs, which today are being built using BGP, into our backbone networks. As we move to an edge that's comprised of a class fabric, that's a new problem in terms of link announcement in the network. The other thing that we're starting to see here is a desire to build kind of core routing or large backbone elements, effectively logical backbone elements, out of a bunch of small discrete devices. Where you might even have a vertically integrated fridge design as a component to this, but you're surrounding it with a bunch of service complex devices or edge peering devices which have different behaviors on them. So we're kind of evolving towards these super nodes that are built out of leaf spine or class fabrics, and we need to hide the guts of these super nodes as we're building the balance of the network out. We get kind of all those best of breed elements if we're building the networks in this way. We can pick the right ASIC for a particular application. We don't have kind of line card considerations inside of a chassis, but we still have to pay the price somewhere else. So what do I get from a link state protocol? Well, I get all of the dirty secrets of what the link is capable of. I get to know things like if I'm using SRLGs, what's the fate that this might have if it's associated with a particular transport system. I know what, if I'm using segment routing, I need the IGP to distribute label information so that I can actually forward at the data plane and construct my data plane correctly. If I need to do any sort of traffic engineering, I need to be able to flood the availability of whatever that traffic engineering application is pervasively throughout the network domain. If I'm going to use next-gen multicast with beer, I need something to do this topology discovery. And if we start to partition the network into different levels or into different areas, we start to make trade-offs in terms of how accurately we can place traffic across paths into the network. So there's a lot of operational value in terms of being able to get at the actual state of the topology at its lowest level. And like we've all partitioned our networks either using OSPF with different areas or using L1 in adjacent elements in order to scale our ISIS domains. But when we do this, we're creating new availability concerns, and we can't traffic engineer into those domains. So what's the core problem? The core problem is flooding all of this information. When there is an update to our topology, we flood that out from the perspective of the originating node, and we flood that out in a split horizon model. This is all the worse when we have thousands of links in the network. We've gotten around this today by being very careful about this, keeping the link counts relatively small, but this is really just for stalling convergence. And just to provide a picture as to how bad this actually is, it's not it's not end of the world bad in today's networks, but if we look at the traditional flooding on the left-hand side, where we inject an announcement and we have to replicate that announcement to all the links where we didn't receive it. we have a pretty big combinatorial problem here that just kind of keeps compounding. But if we look at what would be necessary to actually establish an understanding of the graph, we really only want to be able to get reachability to we only need to flood on a subset of the links. It's not necessary for us to flood every link with all of the information and drop the duplicates. So one of the things that we need to do is we need to figure out how to intelligently, this is not building as nicely as I thought. We need to figure out how to intelligently flood information about the state of our topology on the necessary links. So I'm going to kind of segue briefly into how this problem is being addressed inside of the data center. And there's three protocols that I'm going to talk about here. One is Rift, which is routing in fat trees. One is Open Fabric, which Russ White has worked on and is actually integrated into free-range routing. And the third is LSVR, which is kind of the love child of BGP and link state information. I'm curious to know if anybody's seen an implementation of this in the wild. But when we talk about routing in fat trees, this is born out of some work that Tony Prisgita has done at Juniper. And it's taking advantage of the fact that data center network topologies are symmetric topologies. So when you have symmetry, you can do a ton of optimization. So if you have a special topology, you can have a special protocol. In addition to this, you can take advantage of the fact that you have visibility into the guts of the topology to do novel things. You can see some semblance of traffic engineering by determining how you want to steer traffic over certain prefixes or over certain links. So what's attempted to do, what he's attempted to do here, and I think he's done a great job, is to take the best parts of BGP's distance vector approach and do some smarts in terms of flooding information so that you don't overload the network with flooding topology information. I should point out that there are two implementations of this. Juniper has a trial implementation of this that you can download from the website. And the link is in the presentation. And there's a Python implementation on GitHub, which has been hacked on at a number of IETF events. And they've demonstrated good interoperability. This work has actually generated its own Rift working group inside of the IETF. So there's actually a number of folks who are working on this. And its operation is pretty novel. It's effectively link state flooding from the leafs of the network through the topology up northbound. And then it is distance vector in the southern direction. It does have this notion of bouncing off the lower layer in order to be able to detect and determine whether there's a need for prefix deaggregation. So if you have a break in the network, you can actually use lower tiers of the network and announce a more specific in order to keep the traffic localized at that particular layer in the network through the bounce signaling that takes place. From the perspective of reaching other devices, you have a distance vector behavior. It's sufficient to generate a default and announce that to your devices southbound. And then there's the option of also overloading this with, it's called PGP in the spec. It's policy-guided prefixes so that you can actually do some steering of traffic and actually do asymmetric loading of the fabric. It should be obvious, but probably bears noting that this won't work in a WAN. It won't work in an arbitrary topology. So if you need to interconnect to the rest of the world, you're going to have some border elements which summarize whatever prefixes are being used inside of this environment and announce those to the world at large using whatever your favorite WAN IGP is of choice, or BGP if appropriate. The next protocol here is Open Fabric, and Open Fabric attempts to reduce the amount of flooding that's used in class topologies and strip down ISIS in order to simplify a number of things. So notably, it gets rid of some of the additional bits like being able to announce traffic engineering information. It does streamline the hello process for bringing link adjacencies up. It does streamline the process for flooding information. It doesn't flood as aggressively as ISIS normally will. And it does have the ability to do kind of automatic stage detection But it should be noted that, again, this is dependent upon a symmetric graph, and it cannot be commingled with a standard ISIS implementation in operational deployments. There is a free-range routing implementation of this, which has all of the bits available for Open Fabric operation if you're keen on kicking the tires on that. Again, this is really only applicable in a data center environment. If you want to announce and get to the rest of the world, you're going to have gateway leaf elements which are capable of announcing those prefixes and getting traffic out of the network, out of that particular network. LSVR is an interesting beast, and LSVR is effectively taking additional information from BGP link state, adding a few new TLVs and NLRIs, and extracting the topology from the network using BGP-LS so that you have all of that link state information at your disposal. So you kind of get the richness and visibility of what the individual links are capable of doing, but it overloads the operation and semantics of BGP-LS in some interesting ways. It defines a new link type, NLRI, and it also defines an SPF NLRI. So based on whether you see modifications in the BGP link state database, you can trigger an SPF calculation and you can influence the forwarding decision and distribute this information. So you're changing the behavior of a well-known protocol in order to achieve the scalability aims by taking advantage of the fact that you've got BGP at your disposal, and in theory, one could upgrade your network from BGP as you know and love it today in your existing data center environment and realize the benefits of LSVR. But what we have here is an interesting new protocol. I would hesitate to call it BGP purely, and I don't know that you can really say that you can upgrade to it. So like this one remains to be seen in terms of adoption. I'm not aware of any implementations in the wild, although Arcus is a large, big proponent of this particular protocol and its mode of operation. And I'm curious to see how adoption looks on this front. Again, this is very specific to the operation inside of a data center, and it's not useful in kind of generally applicable topologies. So it's very much a data center-centric protocol. Now, I'd like to take a moment here and pause and talk about a more generalized approach. One of the things that all of these three protocols really have is a constraint in terms of their operation. It's great if I'm sitting inside of a data center, and that's it's a homogeneous environment that I only need to worry about talking to devices of my kind. But this doesn't solve our problems going forward in terms of being able to scale backbone networks or to build edge networks more efficiently. So there's three drafts I'm going to talk about here. Draft IETF LSR dynamic flooding, which kind of addresses the elephant in the room of the problem space. And then two other drafts, ISIS area abstraction and ISIS hierarchy. The focus here is pretty much on ISIS. Because, frankly, it lends itself well architecturally to some of the modifications that are being proposed, and it's very well deployed in service provider environments. So one of the things that the working group decided to do was look at what the requirements are in terms of assembling optimizations on the flooding protocol side of things. So it must provide a dynamic routing solution. So it must behave more or less like your link state protocols do today. It has to improve convergence. It has to address a variety of dense topologies. This cannot be restricted to just bipartite graphs. It must be usable in a general service provider backbone or environment of an arbitrary topology size. It must address multi-stage class and variations, fat trees and such. But demonstrating complete graphs, that being an arbitrary topology, is really a core objective here. There must be no single point of failure. It can't be dependent upon an external controller. And then we need to find a way to treat dense topologies as kind of subgraphs or like discrete components that might be hidden from the balance of the topology. And when they're operating in this, this mode of operation, they can't really radically change the rules of operation. And oh, by the way, if it fits in with what we're doing from a current link state protocol perspective and the flooding behavior is there, so much the better. So the dynamic flooding draft, which just got bumped earlier this week in terms of rev, has what we call a centralized mode. And that's, by that, it elects on the network an area leader. And this is kind of, this follows your DIS or designated router election semantics. There's a few differences here in terms of its operation. And what this area leader is responsible for doing is for flooding flooding the overall system topology across a subset of the links. So it is not necessary for all of the nodes to flood all of the information. A separate flooding topology is to be computed, and then this area leader is responsible for assembling and disseminating the link state information on that topology. This could be computed in advance. This should not hold things up. But this is an on network calculation and election. So we've done some simulation in terms of what's the actual flooding reduction that we see in dense topologies. We've done this across a wide range of scenarios. This graph depicts kind of the variables at play if you look at your standard leaf spine topology here. On the x-axis, apologies for the eye chart, is the number of leaves in the network. You can think of this as the number of racks in a given topology. On the z-axis, well, I should use the right-hand coordinate system. So like, yeah, it would still be z. Is the number of spines. So in coming from you towards the back of the graph is an increasing number of spines, and then the y-axis here is the percentage of improvement. So what you see here is like there's not a whole lot of flooding reduction to be realized when the size is small, right? Like in a small leaf spine architecture, like you're not getting killed by or eaten alive by flooding, but when you get to about 100 leaves. Like you get to some pretty significant reduction in terms of flooding overhead, and we can reduce the flooding overhead by nearly 95%. So as you build out to thousands of racks, this is a massive reduction in flooding overhead and allows existing platforms to keep pace here. We've also run these scenarios against about a few dozen service provider backbone environments. In some environments, candidly, the gain isn't that great. If I'm just going east or west out of a POP, there's not a whole lot of flooding reduction that can be achieved. But if I build out, if I've got a fair amount of fan out in a given metro, or if I have a fair amount of parallel links between markets, I can see a significant flooding reduction. In some cases, almost as good as what I might see in a densely connected data center environment. The next area is, no pun intended, is area abstraction. So right now, ISIS areas are transparent. You see everything that is going on inside of an area from the perspective of elements inside of that area. But one of the things that we think we should be able to do here is we should be able to treat ISIS areas as being atomic. So like I should be able to take a whole bunch of devices which might be in a given POP or associated in a given service cluster, and treat them as if they are a single transit node. So they are effectively looking like a single router. And I want to hide all of the links that are in that service POP from the balance of the network topology. So I can treat these things as, I want to be able to treat these things effectively as opaque elements in topology. And that lets us do some interesting things, and it also lets us start to stitch together data center fabrics across data center fabrics. So if I look at a big leaf spine topology here that might be indicative of a large distributed campus environment, I've got a whole lot of tiers, I have a whole lot of links, but I should be able to get from link to link. I should be able to get from DC spine to DC spine or DC leaf to leaf, and treat these as opaque forwarding elements and I can collapse the visibility I can collapse the internal topology to something that is hidden. The other thing that we can do here is we can look at taking advantage of some of the capabilities that are already existing in ISIS to hide the topology from the world at large and still provide transit functionality. And so what we can do here is take advantage of the fact that there are 6 additional bits for level definition inside of the ISIS PDU, and use those as a mechanism to hide the topology, the internal topology, and still treat the edge nodes as something that I can forward across. There's still a fair amount of work to be done here because I might have protect paths that are internal to a topology that I don't want to expose. I don't have flooding. There's still work to be done in terms of how I go about hiding this flooding, but I can get to a point where I can make intelligent path decisions across different layers in the ISIS topology without having to flood all of the links everywhere and treat these as opaque nodes. Eventually I get to a point where I can have a different level and I can hide multiple tiers inside of that level. I should point out that these are ISIS-specific enhancements that I talked about. This work is really geared towards upgrading our current IGPs and interoperating with our current IGPs such that we can really scale our networks and get beyond having to collapse this into nodes that we have to deal with as brittle edge boundaries. We do not see a desire to merge BGP and IGP capabilities. We've enjoyed a nice world where we can have topology definition and resource availability accessible at the IGP level, and then do service provisioning at the BGP layer. But at the end of the day, this this dynamic flooding is just really fixing mesh groups, which we've had in ISIS for a long time, but we had to judiciously create manually. This automates the process, and it there's a huge win for us here. So this is like the first big piece of work to be taken off the table. The other bits are really nice things to come, and that's additional protocol hardening. So I thought I'd close on a bit of a comparative analysis here. All of the first 3 are really applicable only in the data center. The last one, this dynamic flooding work that we're doing, that's being done in the IETF, and we're doing a fair amount of this work ourselves, is around really addressing the general use case. It has immediate applicability inside of data center environments, so we can now start to look at building data centers using IGPs again. It's definitely an area for exploration and taking a peek at if you're interested in poking at this and tracking the work. More generally, we think there's a lot of utility in a protocol that exhibits the scaling characteristics that folks need for data center environments more widely in the WAN. And these scale-out behaviors that we see in the data center are starting to leak more pervasively out. We want to find a way that we can incrementally enable scaling of the network while leveraging the deployed base that we have there. So that's what I have, and I think we just finished on time. Are there any questions?